Boa tarde. Hello to all. Welcome to the afternoon talk, the last talk in this day, in our UFSCar summer webinar on PDEs. Let me inform you that if you have any question or remark along the talk, please write it down at the comment place in YouTube. You should log in to do it. I'm very pleased to introduce our speaker, Professor Claudianor Alves, from Federal University of Campina Grande, Paraíba, Brazil. Professor Alves has been working in PDEs, mainly on elliptic PDEs, whose approach demand techniques from nonlinear functional analysis, variational, and topological methods. He has by now more than 200 published papers, and has taken part as editorial board member in several journals. Today, he's gonna talk about normalized solutions for Schrödinger equation with critical growth in Rn. Welcome, Professor Claudianor Alves. Very nice to see you. Thank you for having accepted our invitation. It's a pleasure to have you in our webinar.
Thank you, Gustavo. For me, it's a pleasure to be here, and I would like to thanks for inviting me to participate in this meeting. Okay, thank you very much.
Okay, thank you, Professor. Our pleasure. Please, we now can pass to the beginning of your talk, Professor. Please.
Can you see my screen?
Yes, very clearly, Professor.
Okay. So, more one time, I would like to thank the organizing committee by invitation, in particular to Gustavo, Adair, Olympio, and another guys. Thank you very much for your attention with me. Today, I will talk about a normalized solution for one Schrödinger equation with a critical growth in Rn. This is a joint work with my dearest Olympio and Xiaoxi from China. Okay, and here, okay, we have the model that we will talking about. Okay, the existence of normalized solution that we will talk to in this moment is related to problem 1. Okay. This problem 1, of course, is associated with standard wave solution for nonlinear Schrödinger equation 2. And in this talk, I will show for you one result that involves two types of nonlinearity. The first one, the nonlinearity f has one exponential critical growth when we are working on dimension 2. And another result, when we are working with dimension bigger 3 or equal to 3, the nonlinearity f has this form. You can see that f is one sum of two power, where one of them is the critical Sobolev exponent. And here, the power q lives in this interval 2 plus 4 over n 2 star. Okay, here we recall for you the definition of one standard wave solution. When you put this type of function in this nonlinear Schrödinger equation 2, you get one elliptic equation of the form 3, okay, where lambda is the number that appear here in the definition of the state in wave solution. Of course, there is one rich literature involved the existence of non-trivial solution for this type of elliptic equation 3. For example, you can try to find non-trivial solution for this type of problem by using variational methods. Now here, you have the functional J lambda, is the natural energy function associated with this class of equation. When you find critical points for this functional, in fact, you have non-trivial solutions for problem 3. One important class of solutions involving the equation 3 is called ground state solutions or last action solutions. But when you try to find ground state solution, you know what is the value of the parameter lambda, okay? But another important class of solution is when the solution has one prescribed mass. What is mean? What is mean? You fix the L2 norm and you try to find one solution for this equation here. But in this case, lambda is one unknown parameter, okay? In your case, lambda, in fact, is related to Lagrange multiplier that we find when we use variational methods. Here, I would like to talk a little bit about one very interesting paper due by Jian. This paper was the main motivation to study this type of problem. In 1997, Jian studied the existence of normalized solution for this type of problem. Okay, normalized solution, as I said here, it's very important because this type of solution is strongly associated with conservation of mass. Well, in order to find one solution for problem 4, Jian used variational methods. For example, here, Jian assumed on the nonlinearity G the following technical condition. Jian fixed two important constants, alpha and beta, and assumed that the function G and its primitive satisfy this inequality. One example of one function G that satisfies this technical condition is this simple function here, g of x equal to norm of x power q minus 2s, with q in this interval here, okay? When n is bigger than or equal to 3 and q is bigger for when you are working dimension 2. The idea is to find critical points of the energy functional restrict one specific manifold. I will show for you later on. And here, of course, in order to get some compactness, Jian worked on the space of the radial functions. Here, we have the energy functional associated with the problem 4, okay? And this, the idea is to find one critical point of this functional restrict to this manifold S of A. This manifold is exactly the sphere in L2 intercept with the Sobolev space H1. Here, maybe the problem seems easy, but it's not easy, because if you look in details this functional, you can see that you lose the part involving the L2 norm. The L2 norm does not appear in the definition of the energy functional, but it appears only the manifold SA. This type of situation brings a lot of difficulty when you try to prove, for example, that the Palais-made sequence associated with the functional I on this manifold SA is bounded. In order to overcome this difficulty, Jian introduced one very, very nice framework. The idea of Jian was the following. Jian considered one new functional I tilde like this, and Jian proved that the functionals I and I tilde satisfy the mountain pass geometry, okay, after one technical computation. One important thing involving the both functional I and I tilde is the fact that the mountain pass level of this functional are the same. Okay? Using this fact, Jan established the existence one very nice PS sequence for the functional I tilde associated with the mountain pass level, and using this specific PS sequence, Jan built one specific PS sequence for the functional I. But what is the main point in this type of argument? The new sequence that Jan get is more rich because this sequence has more properties that permit to prove that PS sequence is in fact valid. But of course, this is one difficult, but there are another difficult. For example, you know that, for example, the PS sequence is bounded. One question is, well, the sequence is bounded, so to go one subsequence, this sequence is weakly convergent, okay? And of course, the natural candidate to be one solution for our problem is the weak limit. But associated with the weak limit, we need to solve two problems. First one, we need to prove that the weak limit is not trivial. The second one, we need to prove that the weak limit belongs to manifold SA. Okay, in this moment, when the Jan intend to prove this quality involving the weak limit, it is necessary to restrict his attention for the space of radial functions, because in this space we have more information. But in this space, the problem is not easy to solve, because, for example, this manifold is not closed via weak topology. It's not closed. Okay, it is necessary to develop some strategy to prove that, in fact, the weak limit belongs to this manifold. After to prove the boundedness that the weak limit is non-trivial, okay, after some computation, Jan proved that the weak limit is in fact one solution for the problem. Okay, here in this paragraph, I call for you what is the technical difficulty, because here we cannot use the Neher manifold technique. Okay, we have a difficulty to prove the boundedness of the sequence and so on. For this type of problem, okay, Jan, for example, talked for us in the summer meeting, USP São Carlos, and Jan talked about this type of problem. Here I will recall some important facts involving normalized solution. One important number in this type of problem is the number Q bar. Q bar is the number 2 plus 4 over n. This number is called L2 critical exponent. Okay, when you fix your attention on the model G0, when you fix your attention in this model here, we say that the problem is L2 subcritical when the power Q belongs to this interval, 2Q bar. We say that the problem is supercritical L2 when the power Q belongs to this interval here. Okay, this number Q is a very, very important, because dependent of the position of the power Q with relation Q bar, the geometry of the energy functional is totally different. For example, when you fix your attention in this model here, in this model, like 1 power, if Q belongs to Q bar, it is possible to prove that the energy functional is bounded from below and coercive on the manifold SA. This is a very important, because in this case, it is easy to prove that the minimizing sequence is bounded. In this case, it's easy. This type of approach involving minimization technique was introduced in one seminal paper by Stewart. But when you assume that the number q is after or between q bar and q star, the geometry of the functional is totally different, because in this case, the energy functional is not bounded from below. In the paper by Jian proved that the energy functional satisfies the mountain pass geometry and proved the existence of non-trivial solution. In very, very interesting paper by Nicola Suave, the author studied the existence of normalized solution when the nonlinearity is this form. Okay, we have one sum of two subcritical power in the Sobolev sense, and here Nicola assumed that Q is L2 subcritical and P is L2 supercritical. In this paper, due to solve, it is proved the existence of two solutions. One solution is obtained by essentially is study the behavior of the functional by using one Porojaev identity, and so split the Porojaev identity in two parts. In one part, they get one solution, in another part, they get another solution, okay? When you work with this type of nonlinearity, but supposing that P is equal to 2 star, we have one paper by Grande, Ili, and in this paper, the authors prove the existence of ground state in the normalized sense when Q lives in this interval. In this case, L2 subcritical case. Recently, in one very interesting paper, Jian Li established the existence of one second solution. Okay, in some sense, Jian, okay, complete the study made by Soave, because Soave studied this case by supposing P subcritical, Sobolev, and Jian put here the critical Sobolev exponent and prove the existence of two solutions. In another interesting paper by Soave, the author studied the existence of solution for this class of problem by supposing P equal to 2 star. And in this paper, okay, look here, Q lives in the interval 2 star. In this paper, Soave studied the L2 subcritical case, the supercritical case, and the critical case, in the sense L2, okay? And work with the critical case, because they assume that P is equal to 2 star. In this case, so establish the existence of solution, okay, for this range of Q, but in result, they assume these technical conditions involving the parameter mu and the number A. I recall for you, the number A is the number that we are fixing to get the normalized solution. Okay, by using this technical assumption, so establish the existence of solution for Q between 2 star and P equal to 2 star. Here, I show for you some reference involving normalized solution. Of course, here is not one complete list. You can find more results involving this type of subject, but we have a very, very interesting papers do a Bart, Jan, Solve, Bart, Molly, Reese, Vecini, etc., etc. Okay, we have this list. Here, I show for you Morrison then, a reference involving normalized solutions. Here, I show for you what is our main contribution for the critical Sobolev case. That is, when the dimension n is bigger than or equal to 3, and in your case, the power q is L2 supercritical. In the Theorem One, we prove the existence of solution when the parameter mu is large enough. There exists one mu star that depends on the number A, such that if mu is bigger than or equal to mu star, you have one non-trivial. Non-trivial, does not make sense because in the L2 norm is equal to A, one solution for our problem. What is the main contribution of Theorem One? The main contribution of Theorem One is associated with the fact that it complements one result dual solve, because I talked to you a few minutes ago that the paper of Solve, the author assumed this restriction involving the parameter mu and A. In your result, look, the parameter mu, okay, can be large enough, while in the paper of Solve, the parameter mu cannot be large enough. In some sense, we complement because the conditions on the parameter lambda are totally different. Here, it's very important to talk a little bit about the approach used in your paper when we compare with the approaches used by Solve. In the approach used by Solve, the author used the variational methods and they explore the properties of the Pohorev manifold. While in your case, we work directly with the mountain pass geometry, okay? Probably the fact that we use different technique produce different conditions on the parameter mu. But one important novelty for this class of problem is the case n equal to 2. Because in the present paper is the first paper that normalized solution is obtained when the nonlinearity has one exponential critical group. In all the literature until moment, the people does not work with f being one exponential critical group or subcritical exponential group, any result. But here we prove the existence of normalized solution when f has one exponential critical group. Here I recall for you the definition of one function f with exponential critical group. It is well known that the literature involving the elliptic problems and quasi-linear problems whose the nonlinearity has one exponential critical group is very large. Here I show for you some reference involving this elliptic and quasi-linear elliptic problem whose the nonlinearity has one exponential critical group. But I repeat for you, this is the first paper that the existence of normalized solution is considered when the nonlinearity f has one exponential critical group. In your case, we assume this condition on the function f. Okay, this is in some sense, is natural for this class of problem here. Okay, condition on the origin at infinity and Brosset Rabinowitz, like this. And our second theorem say that the problem has one solution when the number A associated with the L2 norm, the number A is fixed. When the number A lives in this interval 0, 1, it is possible to find one normalized solution, again, when the parameter mu is large enough. Here, I show for you what is the idea used in the proof of Theorem 1 and 2. And the Theorem 1, the main tool concentration compactness principle due to Lyon's, while in the Theorem 2, of course, is the Schrödinger inequality developed by Cal. Here, at the moment, we need to restrict our attention to space of radial function because we need to get more information about the PS sequence. But of course, we don't lose anything when we work with H1 rad because we can use the Palais principle of symmetric criticality to conclude that one critical point on the space of radial functions is in fact one solution in whole H1. Now, I will talk a little bit about the idea involving the Theorem 1, the critical Sobolev case. Here, SA is this manifold, J, the energy functional, okay? Here, we consider this map. This map was introduced by Jian, and using this map here, we introduce one new functional, J tilde, and we prove that this functional J tilde and the functional J satisfy the mountain pass geometry on this manifold SA. In order to prove this, here is the definition of the best constant S. In order to prove that the both functional J and J tilde satisfying the mountain pass geometry, it's crucial to establish this behavior here, which is proved in lemma 3. We have this behavior with relation to the parameter S. When S goes to minus infinity, we have the gradient of this function in L2 norm goes to 0, the energy goes to 0, and here, when S goes to infinity, we have this behavior. When we have the lemma 3 in your hands, it is possible to prove more two technical lemma, such that these lemmas permit to establish the mountain pass geometry. Here, I fix the mountain pass level, the gamma mu here, okay? And again, I recall for you that this mountain pass associated with the functional J is the same of the mountain pass associated with the functional J tilde, okay? Because we need to check that in the paper due Jian, when we fix this both functional and prove this equality, it's not necessary to work with a critical Sobolev group, subcritical Sobolev group. It's not necessary, okay? You can repeat all the estimate. Well, one very, very important point is the lemma 4. We prove that the mountain pass level goes to 0 when the parameter mu goes to infinity. It is well known when we are working with critical problems, it is necessary to establish some contour involving the mountain pass, because of course we have one difficulty to establish the PS condition. In this type of problem, this type of behavior is a very, very important to localize the mountain pass level in one correct interval. Using, okay, the deformation lemma, it is possible to find one PS sequence associated with the functional J tilde, given by, denoted by Vn Sn. And when you use this application here, H, capital H, to get one sequence UN, you prove that this sequence UN is in fact one PS sequence for the functional J. But what good properties has this sequence UN? In fact, when you look for the details involving this sequence, of course, you have that this limit 8, this limit 8 is not new. It's the definition of the derivative when you restrict the subspace of the manifold, okay? And here is exactly when you introduce 8 for elliptic equation, the tangent space, sorry, here. And we have a very, very, very interesting limit involving this sequence, the limit 10, okay? The limit 10 is the main contribution that the functional J tilde brings for us, because we get this limit when we study this limit here, okay, in the end of the slide. When you study this derivative, you get this limit 10. So when you use 8, 9, 10, we have one set of good information on the sequence UN. Related to lambda n, of course, when you use this information here, you have, of course, sorry, you can use all this information to conclude that UN is one bounded sequence. Okay, this is a very important. Again, I repeat for you, the fact that to work with the functional J tilde is a very, very important, because they give for us this additional condition on the sequence UN. The lambda n, okay, is almost the Lagrange multiplier, satisfy this inequality. Now, I will show for you very, very important estimates that it was necessary to do in order to prove that the weak limit of the sequence UN is in fact non-trivial in one solution for our problem. The first lemma is the lemma 5, and we establish this important estimate from above involving these integrals, okay? The lemma 6 and 7, again, we have this important estimate involving the L2 norm of the gradient of UN. And the lemma 7, we established two important information involving the sequence lambda n. Because here, what is the difficulty? Because we don't know any information about the sequence lambda n. So here we have this information, and again, look, we have one estimate from above involving the mountain pass level. The localizing of the mountain pass level, it's crucial in your case to conclude that our sequence UN has one non-trivial weak limit. Okay, until moment, we show for you all this lemma. In all this lemma, it's enough to work with the H1 Sobolev space. But in order to prove that the weak limit is non-trivial, it is necessary to restrict your attention to space of the symmetric functions. In this case, when you restrict your attention to radial functions, of course, it is well known we have the limit 11, okay? And we have this limit when the U is the weak limit of U. And the lemma 8, we was able to prove that when mu is large enough, the weak limit is not trivial. This is a very, very important step in your argument. Next, we prove that, in fact, when mu is large enough, it is possible to prove that you have one strongly convergence in L2 star sense. In this case, the concentration compactness principle de Lyon's apply one important role in your approach. Okay? The proof of Theorem One here, we would like to prove that U is in fact one solution for our problem. So we need to work to prove that the normally 2 of u is equal to A, and of course u is one solution of the PDE when you put the Lagrange and multiply lambda A in the problem. So here, using the fact that u is non-trivial, and of course the fact that you have this strong convergence here on the space L2 star and on the space LQ, you have one strongly convergence involving the primitive f of our nonlinearity. This inequality permits to conclude that the lambda n converge for one negative number, lambda a. U is one solution for this equation 13. Using the fact that U satisfies this equation, we get this equality here. Now, using the properties of the sequence UN, you can change lambda n by lambda a, because you can change the order here. You can take the limit in the right side of this equality to conclude that in the last line that this limit holds. But if you look for this last equality, when you use the fact that lambda a is negative, you have here one norm, one equivalent norm to usual norm in H1. So we can conclude that the sequence UN converge strongly in the space H1. Of course, when you use this convergence, you can conclude that the L2 norm of the weak limit is equal to A. This established the proof of Theorem One. In order to show for you the idea of the proof involving the Theorem Two, we need to start our talking in this case by recalling the very nice Schrödinger inequality to Dao-Min-Kao. And here I recall for you the statement of this Schrödinger inequality. When we use this Schrödinger inequality, after some technical computations, it is possible to prove that if you have one sequence, formed by radial functions, such that this sequence lives on the manifold and the norm, L2 norm of the gradient of UN satisfy this inequality, it is possible to prove that this limit holds in L1. As one consequence of the lemma 11, we have the corollary 12. In this corollary, said that you have one sequence that satisfies this inequality here, okay, or this estimate. It is possible to prove this very, very important limit. The primitive of f un converge for primitive of f u in L1, and f un converge to f u in L1. Okay, this is a very, very important technical result in your approach. Of course, the methodology used to solve the case when n is equal to 2 is similar to the case when n is bigger than or equal to 3, in the sense that we prove that the energy functional for dimension 2 also satisfies the mountain path geometry. Of course, the estimate is totally different, because in the first case, we don't use the Schrödinger inequality, while in dimension 2, we need to use the Schrödinger inequality in all the estimated that we done in whole this section involving the dimension 2. Here, we prove again this very nice behavior involving the mountain pass level. The mountain pass level, in fact, goes to 0 when the parameter mu goes to plus infinity. Again, when we analyze the geometry of the functional J with the functional J tilde, again, we have one Palais-made sequence for the functional J tilde that produce one very nice PS sequence for the functional J. And why this sequence is very, very important in your approach, because when you get this sequence using the functional J tilde, we have the limit 16. This limit 16 is crucial. It's crucial because when you use it together, the limits 14, 15, and 16, we have that the sequence is bounded. Of course, when we were work with dimension 2, the boundedness is not enough to use a Trunde-Gamboa inequality. It's necessary to be careful. It's necessary to be more precise. What is the estimate from above that you get involving the L2 norm of the gradient of the sequence? Here we have lambda n is almost one Lagrange multiplier. And again, we make one careful analysis involving the integral of the primitive of the function f, and we establish this estimate from above. In the lemma 15, we prove this estimate, very, very important estimate involving the L2 norm of the gradient of un. Look, this estimate is very important because we know that the mountain pass level, gamma mu, can be choice small. So when we fix mu of one convenient way, we have that the right side of this estimate can be small. This is a very, very important to use the Trunde-Gamboa inequality. Like, this is the fact that we use to conclude this estimate here in the lemma 15. Again, we produce important estimates involving the sequence lambda n. Again, until moment, it's not necessary to use that the sequence is radial. No, it's not necessary because you use only the Sobolev continuous embedding. But in this moment, okay, we need to conclude that the weak limit is non-trivial. From now on, we restrict our attention to space of the radial functions to get these very important limits involving the nonlinearity. So if you suppose that the weak limit is non-trivial, we get this limit. This limit combined with limit lemma 16 prove that the limit superior, the limit sup of the sequence lambda n, it's non-negative, it's non-positive. And using this information, you can obtain one contradiction because we will prove that the L2 norm goes to 0, but it is impossible because when this limit goes to 0, you conclude that the mountain pass level is equal to 0, but in your paper, of course, in the most paper that we know, the mountain pass level is strictly positive. So, in order to conclude my talk and the proof of Theorem 2, we have this equality involving the sequence lambda n. We have very, very nice information on the sequence un that permit to use the Trunde-Gamboa inequality. Have this in mind. We conclude that this limit superior of the sequence lambda n satisfies this inequality, and this inequality is strictly negative. So we can conclude that lambda n converge for one negative number. Again, when we use the properties of the sequence un, you can take the limit to conclude that the u is one solution of this elliptic equation. Here, this sentence 15 is crucial because you can take the limit to conclude this equality here. And Again, like the critical case, we have this equality. We use some properties of the sequence UN. We know that this integral works very well in this situation because we choose the parameter nu of one convenient way that the Schrödinger works well in your estimate. So we have this limit. Using this limit, we have, again, this equality here involving the L2 norm of the gradient of UN. Again, we use the fact that lambda A is one negative number, so this equality say for us that the sequence UN converge strongly in H1. If you have this strongly convergence, of course, you can conclude that U has L2 norm equal to A. Okay, so in this case, I finish here my talk. Thank you very much for your attention.
Thank you, Professor Claudianor Alves, for this very nice talk. Let's see if we have in the audience, some comments or questions. Here we have a question by Professor Andrei Zukin. Instead of using mountain pass, would it be possible to look for minimizer on the set Q of U equals to 0, which is probably a C1 manifold, Professor Alves, please?
Yes. In the papers Dewey Soaf, he used, in fact, the function Q of U. This function Q of U is associated with the Pohorzaev manifold. Okay, it is possible. But in your analysis, when we check the argument explored by Soaf, it was necessary in one specific lemma to introduce this restriction involving the parameter mu and a. In your case, when we work directly with the mountain pass, we avoid that restriction. In this way, we get successful to obtain another type of result that complements, okay, the result do a solve. Our result is not better than solve because we show the existence of solution for another situation involving the parameter mu. One very important question here, I believe that in the future, probably somebody can answer, because look, in the paper of Solve established the existence of solution for mu and one interval 0 like mu1. In the present paper, we prove the existence of solution for lambda bigger than 1 mu2, but there is one gap here. There is no solution between mu1 and mu2. Right now, we don't have one answer for this question, but it's a very, very important question that need to be solved.
Thank you. Thank you, Professor Alves, for answering the question. We can see many greetings, comments on the audience. Congratulations, congratulating you from the talks. I have one question, Professor Alves.
Okay.
Please, if you have used, in fact, a radial framework to obtain capacity, right?
Yes.
Is it possible to prove the results in a non-radial framework? Do you think? What do you think?
Yes. In fact, there is in the literature, there are 2 or 3 papers that the authors does not work with radial functions, because you can use a subgroup of the rotations, okay, and as that way you get the same compactness results. Okay, you can choose don't work with ON, but ON1 cross ON2, and you work in this subgroup and you get one solution that is radial with one part of the Rn is radial with one part of the second part of Rn, but it's not radial in whole Rn. It is possible. So, of course, there is a situation that the people work. For example, in the model that I wrote, we have minus Laplacian of u equal to g of, minus g of u equal to lambda u. It is possible to put next to minus Laplacian u plus potential v of x u. But what is the idea? The idea is to establish a very nice condition on the potential v to establish the existence of normalized solution. Okay, there is one very nice paper, Duebatz, Moll, and other guys that we work with, critical frequency involving the potential V. Critical frequency is when the potential V at infinity goes to 0.
Okay, thank you, Professor Claudianor Alves. We can see here a lot of greetings, comments on the audience. Thank you, everyone, for joining us. And I would like to thank again Professor Claudianor Alves for this very nice talk. Thank you, Professor Claudianor. Bye-bye. Thank you.
Bye-bye. Thank you for your attention with me. Bye.
Our pleasure. Bye. Okay. This talk closes our activities in this day in our webinar. Tomorrow we will resume at 9 a.m. with the talk of Professor Patrizia Pucci. The link to the morning and afternoon talks for tomorrow can be found in the website of the webinar. Here below in the description of this live stream at YouTube, you find the website, the address of the website of our event, our webinar. And there you can find all the links and abstracts and all the information. Please visit there. Hope to see you all tomorrow. Thanks for joining us. Bye-bye.